Okay. So this, I really skipped over what this whole S plane thing is, and I said it's just the plot of those of the complex zeros to the roots of h of s's numerator and the complex poles, which are the roots of h of s's denominator. And it's an attempt, physically what this is, it's an attempt to plot the surface, I'll say depict the surface of h of s. We talk about h of s, this s over s plus 1 or something else. It's natural to wonder what that thing actually looks like when it's plotted. And it turns out that that's an amazingly hard thing to do because s, remember, the variable s is a complex number. So if we were to try to do that, we'd need to have two dimensions to plot it. We'd need to have 2 dimensions just to plot the input. This arrow is going out of the page up here. I'm going to try a different version of that to make.
So, sir, you need 3 dimensions to plot the transfer function?
It's worse. You need 4 because this is complex. And so if you put a complex number into something like s over s plus 1, you can see this is going to be complex. So most functions we've talked about so far, like h of t, time is a real number. It's one-dimensional. Where are we over here? Time is one-dimensional, and therefore we can plot the result of time. Maybe it's the voltage in 1 dimension too. And so we only need 2 dimensions total to plot the relationship. But h of s, if s is complex, it needs 2 dimensions to plot. If the result is complex, we need 2 dimensions to plot. Now we need 4 dimensions total. And I'm not even going to try to draw that, but pretend that this arrow at an angle is going into the page. And so this is the real part of S. And this is the imaginary part of my brain goes faster than my hand goes faster than my brain. That's the imaginary part of S. And now that defines this planar surface. And what we'll have to describe to find h of s is 2 more dimensions, is an extra 2 more dimensions, and we don't have that. So let's simplify it and let's plot just the magnitude of h of s. So now we've got a surface in 3-dimensional space. Imagine a surface over this input surface. And for our particular value that we just plotted, we know that we've got a 0 here at the origin, just continuing on the example I just gave, and we've got a pole out here. And what that physically means, if we were to plot a 3-dimensional representation, is that we've got, at that location, we've got think of a circus tent coming up to infinity over that pole. And then on this side, it's pegged down to 0, and then it's someplace other than 0 or infinity everywhere else. So again, think of what a surface tent, and then it's spread out elsewhere. Think of a circus tent that's pinned to the ground at the zeros, pushes up to infinity over the poles, and that's what the magnitude of h of s looks like.
So is this representatory of a signal, or I mean, how does this apply?
No, really good question. This is a representation of a system. Remember, everything we're talking about here is a system representation. So our transfer function is our system. And so what we're trying to represent, I like the question, is we're trying to represent We already know one representation of a system, our circuit. That's easy. But now we've got a two-dimensional shape embedded in four-dimensional. We've got a two-dimensional surface embedded in four-dimensional space, and that's an equivalent representation of our circuit, which is our transfer function if we were to actually graph it. I'm only showing you this to show you what I think it's interesting to see what an intuitive representation of what h of s is, but don't think of it that way. Instead, the way I want you to think of what an S-plane plot is, although it is truly an attempt to depict the surface of the graph of the magnitude of h of s, I want you to just think of it very simply as that for the particular system that we've described so far in our example. Okay? It's more just of an intuitive idea. But if you want to plot it, you want to convert h of s from its polynomial form, h of s from what it was, which is going to be s squared, c1 s squared plus c2 s plus c3 over a different, I need to come up with a different variable. I'll call it a sub 1 of s cubed plus a2 of s squared plus a1 of s plus a naught. You want to convert it from that polynomial into its factored form, which would be s minus your first 0 times s minus your second 0, and all over s minus your first pole times s minus your second pole, and so on. And now once you find those, you found the zeros are your z's, your poles are your p's, and you can plot them on your S-plane and you're done. And why on earth would you go through this pain? Well, there's a few reasons. One is that it's really easy to see if a system is bounded input, bounded output, stable. And the answer is, are all the poles, we only care about the poles, in the left-hand plane? And watch why. Every pole that's in the left-hand plane, when we do its inverse transform, gives rise, if we have a pole that looks like this at -1, that's equivalent to 1 over s plus 1 as a transfer function. Here's our S-plane. And that's equivalent in h of t to e to the minus t u of t. And it's critical that we notice that this is a minus. So if you hit it with a hammer, its impulse function decays away in time. And that means if you hit it with any summation of impulses, its summation response would have to decay away in time. And since you can make any input x of t out of a shifted sum values of impulses, that means that for any input that's not infinite, you'll get a decaying response. You'll get a system response that eventually decays away. And if you don't have that, say you had a pole at +1, that corresponds to an h of s that looks like s minus 1. That corresponds to an impulse response that looks like s to the positive t, u of t. And now if you disturb it with an impulse, the response will grow to infinity. And since, again, any input can be created as a function of shifted, scaled impulses, that means any input you give it is going to cause the output to quickly go to infinity. So here's another way of finding if a system is bibostable. One way of finding if a system is bibostable is the integral of its impulse response. So one way is So BIBO, therefore, equals either of these two things. One, is the integral of h of t finite, the absolute value of h of t finite, or are all the poles in the left half plane? And that's both equivalent. Or are all the, do all the exponents, let me say this again. Does h of t decay? All equivalent to being bibostable. Thumbs up. But there's more. So one way is to see if a system is bibostable. Another way is, another reason why S-plane plots are useful is it's easy to see how quickly a system dampens or decays. So the farther the poles, we only care about poles with this again, farther the poles are to the left, the faster it decays. And that's because if we have one at -1 and one at -2, that is equivalent to having an h of t at -t versus an h of t at -2t, and this decays faster. And if you think about it, that's really just the same case as what we looked at for number one. What we're saying is that the further to the left the poles are, the faster they decay. That means the further to the right, the slower they decay. And if they flip over from the left half plane to the right half plane, not only do they not decay more slowly now, but they in fact increase and they become unstable. So you can quickly look at a system's S-plane plot and say, man, if we'd like to have this thing decay faster, just push that pole to the left. If we want to have it decay more slowly, push it to the right. If we want to make it unstable, push it into the right half plane.
What would be the reason for wanting to have it decay or make it unstable in terms of like your circuit design? Why would you want to do that?
Yeah. An example of why you'd want a circuit being unstable, I can't think of one off the top of my head, but a different kind of system unstable, it's good to have an unstable plane that you're flying if you want to fly in a dogfight. So most of our modern jet fighters are inherently unstable in their design. If you move the control surface slightly off neutral when they're in flight, it will create the plane will rotate, and the way it rotates will make it want to rotate even faster and faster. So with a small control surface, you can now get extremely fast moving changes. Now then, that means that it's almost impossible to pilot. And so now you've got a very complex system of electronics that compensates against the plane's inherent instability so that the pilot can control it. It's the same type of thing that we have with hyperspeed missiles. If you've seen a Patriot missile flying, it's insane. It can be doing Mach 3, and then it looks like it just does a perfect 90-degree turn in the middle of the air to track a quickly moving missile system, incoming missile. And it's because the missile itself is inherently unstable. So a small control surface change can make it radically change position. And then it's also got the complicated electronics to bring it back to make the overall system stable when you put the electronics back in the loop, even though if you analyze just the mechanics of the missile alone, it's unstable. Make sense? In general, you don't want to have circuits go unstable, though. And so you'd use your S-plane plot to quickly see, we're getting close to the right half plane. We can't move it anymore. The last is, it's easy to see if your circuit or your system oscillates. And it oscillates if you've got an imaginary component of your poles. It's always about the poles. So if we were to pull this pole off the real axis, you can't have a single pole off the real axis. You always have complex conjugate poles off the real axis. Whatever has a positive imaginary component will also have a negative imaginary component. And then you know from our inverse Laplace transforms that then that causes an oscillation. And at what frequency does it oscillate? At that J omega frequency. The further up it goes, the faster it oscillates. The closer to the real axis, the slower it oscillates, until finally it's on the real axis, and then its frequency of oscillation is in fact infinite.